Here we have a large rigid body with forces acting on it, and we're going to chop it up into a bunch of little tiny pieces here, which we'll call MI for each of those pieces. And each piece could have a force on it, which we could call Fi. And we have that shown over here for this force. And we could do an analysis using first moments, and we could locate G, the center of mass. And we saw from our work with particles of systems that if we add all of these forces that are acting, the internals will cancel, but the externals will be equal to M total times AG, where that becomes one of our equations that we can use to analyze the motion of this body. The second family of equations come when we take the moments, and we have an arbitrary axis that we're observing this from called A. So the sum of the moments about A would be the sum of the Ri cross Fi, where Ri is the distance to the ith particle, and Fi is some force that acts on it. And recall, for moments and torques, we need the perpendicular component here to find the torque, or the moment about A, due to that specific force, and that's why we have a cross product in here. And from here we could observe that Fi would be MIAI, which would represent the acceleration of that ith particle. And if we plug that in, we'd have the sum of the Ri's cross MIAI. However, we have to be careful here with AI. AI is A of A plus A of I with respect to A, if we want to be really diligent with this, because perhaps there's some acceleration of A that we'd want to include. Now this M is a scalar, so I can move it over here just to keep it out of the way. And we'll get next the sum of the MI Ri crossed with AA plus the sum of the MI Ri crossed with A of I with respect to A, if we use the distributive property on the two parts of AI. And looking at this, AA is a constant, so it lifts out of the summation, and we're left with just the sum of the MI Ri, which we should recall from our discussion on particles is M total Rg, that's a first moment, crossed with A of A. Now over here, none of these are constants, they're all I specific, and this cross product is interesting. If we look at this ith particle back here, here's our Ri value. There's two types of acceleration that it could have. It could have an R omega squared type pointing towards the center, and it could have an R alpha type that's perpendicular to that if this is spinning with some omega and potentially has some alpha value. And if we think about it, the cross product here is going to wipe that out, and this will be the only part that survives. And what we'll get from that will be the sum of the MI Ri times Ri alpha, the tangential acceleration of that particle, and this alpha is a constant. This becomes the sum of the MI Ri squareds times alpha, where again alpha is a constant, and that will give us the moment of inertia I about point A. So if we put all this together, we get that the sum of the moments about A will be IA alpha plus MRG cross A of A. Now this is a rather important conclusion. This represents our second equation that we can use. And you might recall from your first year in physics that we could say that sum of the torques is equal to I alpha, and we use that equation quite a bit. However, torques and moments are really the same thing, So there's an extra piece of the moment equation that we weren't shown last year, and that's this extra mRg cross A of A. And the reason you didn't see that in your introductory physics is that it was rare to have an accelerating reference frame. To understand this better, let's look at the cases where this term goes to 0 and does not exist. Obviously, it'll be 0 when A of A is 0. If you have a static system that's not accelerating, this term will certainly drop out. The other case would be if Rg were 0. And that would be the case that you're on the centroidal axis. And that's because the acceleration would be acting on that point, whatever acceleration of A that we might have. So it's not going to generate any kind of a torque or a moment about this system. A third case would be where this cross product is 0. And that would imply then that AA and R are in the same direction. So if we have Rg here and the acceleration also happened to be along that path, ideally pushing on G, we're not going to see any type of a torque or a moment. So those are the three cases where that term won't be seen. You have no acceleration of the system, you're on the centroid, or they happen to be in the same direction. Let's look at a case where it's not 0. Let's have no moment beyond the system, and let's just have the system accelerating only. If we see that, this term here, mRg, here's our Rg, times m, just a scalar, cross with A of A, which we'll use this one here. And to cross these, we would cross R towards A. So we're going to get that. However, the full equation says that the sum of the moments about A is IA alpha plus mRg cross A of A. And we're saying this is 0. There's no moments. So IA alpha will be equal to negative mRg cross A of A, which we saw over here would act in this direction, but this negative will reverse that. So we find the alpha will be mRg cross AA over I, and it will be in this direction. And think about that. If we take this system here and just suddenly accelerate it in that direction, this thing is going to rotate with some alpha due to that. And it's an inertial response. So that's what this represents. It represents an inertial moment. That's to say there's an apparent moment induced in the system due to the resistance of motion of this particle up here. If you think about it, say we had a beam hanging from a little wheel with no friction, and we grab it and accelerate the system. This beam is going to rotate backwards as a result of that. And that's our inertial response to this acceleration that's being applied to the system. So that's what this represents. And the cross product will evaluate it for us. And note here, when we write Rg, it's always R of G with respect to A, or whatever value we're using back here when we write that out. Now that represents our second useful equation when analyzing motion, and it's just a longer version of the moment equation you're used to seeing. However, keep in mind that the sum of the moments about G will equal I G alpha, where this is true. If we're taking the moments about G, R of G is equal to 0, and this does not exist. So this equation becomes one of our go-tos. This will always work, and we won't have a cross product to worry about. So these two equations are always valid. And this equation is valid as well, but could involve more work if there's some acceleration of the reference frame. Next, I want to derive an alternate version of this equation, which I'm going to do quickly because the process is quite similar, and if you're really interested, you could slow it down to watch it. Here we'll start with the same moment equation about A that we saw before. And here we saw that Fi could be written as Mi AI. F is equal to MA. And note that Ri here could be written as the sum of the other two vectors. So Ri is Rg plus little ri vectorially. And Ai could be written also as Mi A of G plus Ai of with respect to G. And again, this would account for any accelerations about G. And our goal here is to try to bring the moments about G into this equation. If we put all this together, we get that the sum of the moments about A is equal to the Rg plus Ri crossed with Mi times the acceleration of G plus Ai with respect to G. And now we'll do a full distributive property on this, generating 4 terms. Now the first one's easy. Rg is a constant and Ag are constants. So they can come out of the summation, and the sum of the mi's is just m total. So we'll get that the sum of about A, m total Rg cross Ag for that, plus. And if we want to look for other easy ones here, this is a constant, so that's not inside the summation. The summation is only here. And the sum of the miRi's, where little case r is with respect to the centroidal axis, that's the first moment. And the first moment about a centroidal axis is always 0. So we find that that term is going to be 0. Okay, this one here is a doozy. That's a constant, so we can lift it out of the summation, and it'll become Rg crossed with the sum of the Mi A of I with respect to G. Now this is with respect to the centroid. If we look at our body, the acceleration of I with respect to G has 2 potential types. It could have an Ri alpha type, and it might also have an Ri omega squared type, as this system potentially could have an omega and an alpha associated with it. Knowing that, this will split up into 2 terms, which will be Rg cross the sum of the Mi Ri alphas, and the other one would be Rg crossed with Mi Ri omega squareds. And if we look at that, alpha is a constant. So we really have some of the miRi's here, which is our lowercase r's with respect to the centroid. That is the first moment about the centroid. So that term goes to 0. And over here, omega is a constant for all points on the disk. And again, we see the sum of the miRi's, which is the first moment about the centroidal axis, which is always 0. So it turns out, a detailed look at this, we find it to be 0. And that leaves just this term over here now, which again we can look at. None of these are constants, they're all with respect to I. For this term, we're going to be crossing Ri with Ai with respect to G, the centroid. And if we look on the object, here's G, here's our I, it's shown for us, and we know that we could potentially have an Ri alpha acceleration here, and we could see an Ri omega squared here, and if we're doing the cross product, this term drops out and that one survives. Now recall before, the reason they didn't drop out immediately with this term here, this other value, we were crossing them with Rg. So they both had the potential to survive when we crossed them with Rg. Here, this one definitely drops out. So this reduces to the sum of the miRi's times Ri alpha. We don't need the cross product anymore because we evaluated that. And this becomes, that's a constant, So this becomes sum of the MIRI squareds alpha, and that is the I, moment of inertia, about G. Remember, lowercase r is with respect to the centroid. And it's not 0 because it's mr squared, which by definition is the second moment. And we end up with IG alpha for this term here. So when all is said and done, this equation becomes the sum of the moments about A is equal to IG alpha plus MRG cross with AG. Johnny did it! Which is very similar to the other equation, but it does have an important subtle difference, which we can take a look at now. And here's our fourth equation, where that one's our third, and this becomes our fourth. So we find when we're analyzing motion of rigid bodies, there's one linear equation that we can write and three different ways to write the moment equation, depending on the scenario and where you want to take the moment about. And again, we see these inertial responses inside this system if you're taking a moment about a point that is accelerating. And here we see again, if you're on the centroid, then RG will be 0, and that term drops out and becomes the simplified one where this A would become G since you're on G doing that, and that will default back to 3. However, if you're not doing the moment about G, you're doing it about some arbitrary point A, and there's some acceleration of the system, be very careful. An easy way to remember the form here is whatever term we have here will have the same term parked over here. If we have an A here, that needs to be an A. If we want to do it about G here, that needs to be a G. These equations are useful because there's often reasons we want to take the moments about A, specifically, and avoid G, generally if there's too many unknowns. So if you are forced to take the moment about A, you can do it by trying to minimize the work of this cross product in terms of how you write that equation. So you might do it with respect to G, or you might do it with respect to A. And our examples will show how and why those work. Man, that's a kick in the pants. Here we have a narrow rod suspended by a frictionless pivot up here at a contact point which we'll call C. And mu is 0. The rod has a mass m and a length L. And we're going to impact it with a force F acting a distance h below point C. And we're asked to find alpha and A sub C, the acceleration of point C due to this impact down here. Now, a good place to start is with our free body diagram, where we have F. We know that G will generate an mg weight that acts at its center. And up here at C, we have a normal force acting up, which we can just call N. And that completes our free body diagram, and now we can apply our second law and moment equations to this. So to go after alpha, we can certainly try the sum of the moments about G is equal to IG alpha. That's one of our nice shortcut equations, and we know this one's always valid. It's important to identify a direction for this alpha. So I'm going to say that this will be a positive rotational direction. So from here, our moment will have F times, now the distance from G to F is going to be H, and this will be L on 2 here. So that'll be H minus L on 2. So we'll get H minus L on 2 is equal to IG 1/12 ml squared alpha. And with that, we can find alpha. So alpha will be 12F on ml squared, H minus L on 2. And this solution is interesting in that the location of the force for h greater than L on 2, we're going to get a positive alpha, which means it's going to swing like that. But for h less than L on 2, we'll get a negative alpha, which means it's going to rotate in this direction instead. Now, why is that? Well, if we look back here, if we impact it here, this thing's going to rotate with a positive alpha about that center of mass. But if we impacted it up here, there's inertia to this rod, and as a result of that, it's going to cause it to accelerate and move C forward, and we'd have a negative alpha. It raises an interesting question. What will happen if H equals L on 2? We impact it right at the center of mass of this system. Well, alpha would be 0, which means the rod itself would all uniformly just move forward as a linear event and just slide forward. So with that, we have our value for alpha. Now next, we're asked to find the acceleration of point C. So up here, we'll just guess that this is positive, so that'll be a positive a sub c. And we're working off of an xy frame. And a good place to start, since we'd like to include the acceleration of g in this event, is to write the equation a sub c is equal to a sub g plus a sub c with respect to g. Our relative acceleration equation will help us relate what's going on at c with what's going on at g. And the reason we want to know what's going on at g is the sum of the forces is equal to mag. The other equation that we've got always uses g, so we need to include it in here in order to bring in the forces and their effect on that system. So applying the second law, we have sum of the forces in the x is equal to magx. And we have only F here, so F is equal to magx, and agx is F over m. So we find that the center of mass of the system, no matter where it's impacted, will move forward with a constant a. Now in the y direction, if we look at it, this thing is suspended up here, so there's no reason to expect it to move. So sum of the forces in the y, mag, and we expect that to be 0, so we end up with that mg will equal Fn. Not much else is happening there. This, however, is useful because now we know one of these terms up here. Next, let's look at that. This is the acceleration of point C with respect to point G. So let me draw that. Here's G, and here is C. And for a positive alpha, we would expect the observed acceleration to be an R alpha type in that direction. And there could potentially be an R omega squared type pointing directly at it. However, this thing's at rest initially, so that doesn't exist right now. We really only have that. So we end up with the acceleration of point C as observed from G for a positive alpha is going to be in the negative x direction. This term is negative R alpha of C with respect to G. If we put all these pieces of the puzzle together, we find that a sub c will equal a sub g plus a sub c with respect to g. We know this, it's in that direction, and it's F over m. And we know this is going to be negative R alpha, and R of c with respect to g is this distance right here. It's L on 2. This will be L on 2 times alpha, which will be 12F over ml squared, h minus L on 2. Now, if we do a little work on this, we can pull this 2 out here to the front, and that'll take it out of here. It'll put one into there, though. One of these L's go. So we get the acceleration of c is f over m minus, now we have 3 times 2 here, so we have 6 fh over ml, and then plus 3fl over ml, where here the L over L's can go. And we could factor out an f over m, so we have a sub c will be f over m, and we get 1 minus 6h on L plus 3, and 1 and 3 is 4, so we'll get f over m 4 minus 6h on L. And let's not have a fraction in here. If we pull this L out here, we end up with f over ml 4L minus 6h, which I'll write up here, where that's our solution now for a sub c, and this will be our solution for alpha. And we saw that alpha will be positive and negative. Let's look at what happens here with this critical point. This will become 0 when 4L is equal to 6h, where h0, we'll call it, will be 4/6 of L, so h0 is 2/3 of L. And that's interesting because we have 2 critical spots. We have a 2/3 of L, and up here we found that h critical was 1/2 of L. So there's 2 different ones based on whether we're looking for an alpha or whether we're looking for an a sub c. And let's see what that means. Let's look at alpha first in terms of what happens to it when it's hit at the different spots. And we found for alpha, it's 0 at h equal to L on 2 right here. And below that, it would be a positive alpha. And above that, it would be a negative alpha. In fact, h is linear here. There's no powers in this. So if we want to draw this out, it would look something like that. And that would give us the value of alpha for the different locations where we decide to hit or impact this thing. If we decide to hit it right at G, we just have straight line motion with no rotation at all, so alpha is 0 here. Now, looking at the acceleration of C, the critical point is 2/3, and we find below there, for h greater than 2/3 of L, this is going to be larger than that, and we'll get a negative a in this regime down here. And for h less than 2/3 of L, this will be larger, and we'll get a positive a sub c in that range. And here we could draw this out. It's a linear function. If we impact it in this region, we'll get a positive a sub c, and if we impact it down here, we're going to get a negative a sub c up here at the top. So this is giving us the value of a sub c based on the location of the impact. And what's fascinating to see is right here, a sub c would be 0. Notice that it's not the same point where alpha is 0. This is different. If we strike the object right here, no force at all or motion at all would be imparted to point C at that one instant. It would sit there perfectly still. And that is a special name. That's called the center of percussion. And the center of percussion, which we said is at h equal to 2/3 of L, is the location where the point where no shock will be imparted to the pivot point at that one instant. And if we were holding it here with our hands, let's say, and someone hit that spot, we wouldn't feel anything initially. You'll often hear it referred to the sweet spot. On a baseball bat, if we're holding the bat down here And this is differently weighted, so it's not a perfect rod. However, the label usually indicates the sweet spot. And by hitting the ball here, that's our impact force, you'll feel very little shock load in your hands. If you hit it back here, you're going to feel the force. If you hit it out here, you'll feel the force. But that one sweet spot is the spot where the bat doesn't impart any force to your hands. Now let's take a look at the case where we have friction of mu sub s. We're trying to find the maximum force for it not to slip up here at the top. Our free body diagram still looks similar. We have an mg down. We have a normal force acting up. And we have a friction force now, which we'll guess is in this direction. It's just a guess, and the signs will fix themselves. Now, we might be tempted here to jump in and do some of the moments about g is equal to I g alpha first. But this gets fairly complicated. We've got two forces here that won't drop out. We'll end up with F h minus L on 2 plus the friction force times L on 2 is equal to 1/12 mL squared alpha. And to solve for alpha, we're going to need to extract out this friction force F, which, if we look at this in the y direction, I think you can see that the normal will be mg, and the friction force will be mu mg. However, we still end up with a fairly big equation. Let's try a different approach. Let's do some of the moments about c is equal to I c alpha plus mrg cross ac. Now, at first, this equation does look intimidating, but if it's not going to slip, point C can't move. We have a pinned rod, basically, and A sub C is 0, and this cleans up quite nicely. So we end up with the sum of the moments about point C is simply I about C alpha. And this equation, because we choose this location, won't have the friction force in it yet. So we end up with F times H is I about C, which is 1/3 mL squared alpha, or you could do the parallel axes theorem to get that as well. But we know the rod about the end is that. And from there we get directly alpha as 3F H on mL squared. So even though the equation sometimes looks like it's a mess, it does clean up. And if you have a fixed point someplace, definitely try taking the moment about that point. Also note that this is always positive. No matter where we hit this stick, it's always going to have a positive alpha. And the reason for that is it's pinned, basically. We're not letting it slip. Now, to incorporate the frictional force, we can look at the sum of the forces in the x is equal to magx. And if we choose this as positive, we have F minus the static friction force is equal to magx. If we do that in the y direction, some of the forces in the y is magy. We see that there's no reason for this stick to accelerate up or down and just leap out of the way. There's no real impacting forces in those directions. So agy is 0, and we find then that the normal force is simply mg, which we suspected from the start, which means the friction is mu mg. So this becomes agx is F minus mu mg over m. So that's the acceleration of the center of the system. From here, we need to relate these two things. And the best way to relate them is via a relative acceleration equation. So we can say that a sub g will be a sub c plus a sub g with respect to c. This is done vectorially. And recall, if it's not going to slip, then a sub c is going to be 0, which is nice. So a sub g, which we have here, is equal to A sub G with respect to C. Now let's see what that looks like. G with respect to C is here. This is C, and this is G. So that's G as seen from C. And there's two potential accelerations that we could have if we're watching it from C. Realize that that's constrained uniform circular motion, about L over 2. So we could have an R alpha type for a positive alpha, and we could potentially have an R omega squared type of acceleration. Well, the rod is initially at rest, so we don't have to worry about that. This we could have, and in fact there is an alpha when we impact it. And we'll end up with the acceleration of G with respect to C is R, which is L on 2, times alpha. And it'll be positive by the right-hand rule. So this exists. It's L on 2 times that. So if we relate these together, A sub G is F minus mu mg over m. And that's equal to this, which would be L on 2 times our alpha value, which is 3F over 3FH over ml squared. And one of the L's goes. Both of these M's can go here. And our goal here is to find F max. So let's clean this up a little bit more. I'll bring the 2L up here as well, just to get rid of them. So we'll end up with 2LF minus 2L mu mg is equal to 3FH. Grouping the force values together, we'll end up with negative 2L mu mg is 3FH minus 2LF. Let's multiply through by a -1 just to flip some of these signs around. And we can factor out F here. So we'll end up with this side being F 2L minus 3H. And finally we can solve for F, as F max will be 2 mu mgl divided by 2L minus 3H. And that's the maximum force to not slip. And it's a function of mu, of L and mg, and also the location where we decide to impact this thing. They all play a role in that value. And again, we saw, like we did earlier, this value here, where we could find H critical again as 2/3 of L. And we saw that that was the center of percussion before as well, where if H is greater than H critical, we're going to get a negative F. But actually what we'd have here is we'd have a negative number down here, which means the friction, which we guess to be in this direction, will switch to the other direction. So it doesn't mean that it's a negative F. We're always hitting it with a positive F. It tells us that the friction will switch and be forwards. We had guessed it to be backwards. And for H less than H critical, we get a positive friction force, and the friction is in the direction that we had guessed it to be. So the center of percussion plays a role here as well. What's also interesting is that for H equal to H critical, we get division by 0, which means an infinite force could be applied to the rod and it's not going to move. In fact, if we plot this function out, it looks something like this. And it's interesting to see that at H equal to 0, if we hit it right up here at the very top, that goes to 0, and the 2L will drop out, and we get directly that F will equal mu mg, which is the same force we would find if we were just trying to push a block across the surface. We overcome the static friction and it moves. And that's because we're right here underneath that roller which has friction. And then as h increases, we find the force goes up from that minimum value, and at the center of percussion, it reaches an infinite force. You could hit this with a massive force, and initially this won't move. Now, fractions of a second later, it will start to move as the bar takes off and this gets pulled out of its position. But initially, at the very moment of the strike, this would not feel that impact. We had originally guessed that our friction was going to act in this direction. And we found that if our H was above this location, we were correct. And we would have friction acting in this direction. However, if we hit it down here below that point, the friction switches and becomes a negative friction force in that direction. And that's because we're trying to give it an alpha like this, which is going to cause that end to try to move that way. And friction wants to oppose that motion. So the equations are taking all of that into account. Thanks for watching.